Когда принесут, позови. Я попробую.
Ну, мы, в общем, запустили пока.
А надо, чтобы они потерялись?
Ну, кто-то потерялся.
Пока нам куда-то делать, вот в этом конфликте.
А, ну то есть это так начинает?
Да.
Ладно. А, вот там, да? Все, уже пришла, да?
Но он включен.
Не, я включил. Все работает. Вон, видишь, это звук. Это звук отсюда, по-моему. Нет, это звук от микрофона. Ну вот мы сейчас говорим, и он шевелится. Нет, он, скорее всего, лучше проверить трансляцию. Он здесь захватывает. Наверное, лучше проверить трансляцию. Вот это вот интерфейс цифрового звука.
Раз. Так, ну что-то мы уже очень долго готовимся. Надо начинать. Как, идет звук, не идет? Ну, отлично, все. Well, let's start. Last time we discussed abelian extensions of groups. So I recall that such short exact sequence is called an extension of G by A, and we are interested in abelian extensions, so that A is an abelian group, and then the group G acts on N A by its automorphisms. We have discussed this, and we finished last time I formulated the theorem, and now I recall that the claim is that we consider all extensions with given G, given A, and given action of G on A. So we fix an abelian group, and we fix it not only as a group, but as a G module. So then we consider all extensions of G by A with the given action, with the given G action on A, and we consider these extensions up to equivalence. And I recall that equivalence is two such extensions, this one and this one, are equivalent if there exists an isomorphism which makes the diagram commutative. Well, so this set, extensions of G by A, with the given G actions on A up to equivalence, are in one-to-one correspondence with elements of the second cohomology group of G with coefficients in A, where A is a G module, so we use this particular action of G on A. Okay, this is theorem, and now I'm going to prove this theorem. Okay, but before we prove it, I would like just to mention one important particular case is when the action of G on A is trivial. This is a very important case. Well, on the right-hand side, we see then the cohomology group with untwisted coefficients. But what is on the left-hand side? On the left-hand side, if the action of G on A is trivial. I recall how the action is. If we have, now I would like to erase the second extension. If I have an element A here and an element G here, and I would like to act by G on A, then I proceed as follows. I map A here to E, and I choose a pre-image of G in E, and then I map G acts on A by taking the it is better to write G acts on A by taking by this formula. So I proceed as follows. I map A to E, then I make the conjugation by a pre-image of G. Here G tilde is any element in the pre-image. And then this is just G times A, but it always belongs to the image of this inclusion. So we have a well-defined action. And look, when this action is trivial. This action is trivial if and only if elements of A, well, if I think of A as of a subgroup here, then I can erase this I everywhere. But the action is trivial if and only if elements of A commute with all elements of E. So action, let us fix this. Action is trivial. In other words, it means that if and only if I of A, or we can just say A, yes, if we is contained in the center of the group E. This exactly means if all elements of A commute with all elements of E, this exactly means that A is contained in the center of the group E. And such extensions are called central extensions. This is called central, by definition, this is just name for this situation. This is called central extensions. And they are of particular importance. According to this theorem, they just are in one-to-one correspondence with cohomology classes with untwisted coefficients. So now let us prove the theorem. The proof of this theorem follows the main line how actually homology groups appear. Well, actually, if we look through history, then, well, a good question is in which part of mathematics homology and cohomology first appeared. And this was not topology. This was complex analysis, complex functions of complex variable. Usually there are some homological abstractions to existence of some maps or to something like that. Usually, so the intrinsic sense of cohomology classes is that they are supposed to be abstractions to something. And here we see exactly those situation. Assume that, well, just maybe for a moment, the most clear case is exactly the case of a central extension. Assume that the action of G on A is trivial. then we have such central extension. But what is the simplest central extension which we know? If we take A and G, and the simplest possible central extension is the direct product. We have this trivial situation with obvious maps. But we can have also some non-trivial examples. Similarly, in the case of a non-trivial action of G on A, we have a semi-direct product. And in general case, if we are given the action, then, well, G acts on A, so it is written as in the following way. We have this semi-direct product, and again, we may have some other examples, but how these situations, these simplest situations, can be characterized. What is the characterization for them? The characterization for them is that in these cases, we have a split. The short exact sequence splits. We have a homomorphism from G to here, which is, well, I never remember which is it right inverse or left inverse? Well, which is inverse to pi in the following, so that this homomorphism and then pi is trivial. So in these situations, we have this section homomorphism. And in this and only in these cases, indeed, if we have this section homomorphism, then if we have here a section homomorphism, then G becomes a subgroup of E, and E automatically becomes the semi-direct product of A and this image of G. So these two extensions are trivial, and they will correspond to a zero element here. So our correspondence, which we haven't constructed yet, will be such that zero element of this group corresponds to a semi-direct product. So the idea is that these cohomology classes arise as an abstraction to the existence of such section. So we will try to construct a section, and we will see that in general it is impossible, and an abstraction will give us exactly a cohomology class here. And exactly when this cohomology class is trivial, exactly in this situation, we'll see that a section exists. Well, now how we will construct a section. First of all, of course, the problem exists only if we want this section to be a homomorphism. If we try just to construct a set theoretic section, then there is no problem. This is a surjection, and of course any surjection has a set theoretic section. So we choose any set. The idea is that we choose a set theoretic section, and we will try to transform this set theoretic section to a homomorphism. So let S be S, a set theoretic section. So S is not supposed to be a homomorphism. But of course, it is convenient. We have here a unit, and of course it is convenient to take unit to unit, and there is no problem to take unit to unit. So we will always assume that this section takes a unit, the unit in G to the unit in E. Okay, and well, And now now I would like to measure how far is this set theoretic section from being a homomorphism. How to measure this? The idea is that, well, assume that we have any two element G1, G2 in the group in G, then we can write. I want not to. Well, we can write such an element. Well, what can we say about this element? This is an element of E. Well, if this element was trivial for all pairs G1 and G2, then S is a homomorphism. So this element measures the how far is S from being a homomorphism. But now look, let us take a pi. Pi is this homomorphism from E to G. Let us take a pi of this element. We know that pi is a homomorphism. We do not know this about S, but pi is certainly a homomorphism. So, and we also know that S is a section. S is a section. This means that if we take apply S and then pi, then it is an identity isomorphism of G. So we obviously see that this is applying pi here we see G1, applying pi here we see G2, and applying pi here we see G1, G2 inverse, and of course this is unit. So we obviously see that this element is in the kernel of pi. This means that we can consider this element as an element of A. So this element is I of some element of A, and this element of A is uniquely, well, okay, since this is an inclusion, then we have a unique element of A with this property, and let us call this element of A depends on G1 and G2. Let us denote it by phi of G1, G2. So we get a function phi is a function from G times G to E to A. Well, here we see something which looks like cohomology. I recall that the cohomology is obtained well when we have written this during the last lecture, that if we take usual normalized bar resolution and then we take home from, well, if R P, we denoted P star, is normalized bar resolution, and we take the complex, we take home over G from P0 to A, then we go to home from P1 to A over G, etc. Then the cohomology of this complex is exactly the cohomology of the group G with coefficients in A. And we discussed last time that this group exactly consists, last time we denoted this group by C2 over G over A, well, and I recall that last time we discussed that this group consists exactly of all functions phi from G times G to A, which satisfy certain condition. Which condition? Condition is that delta phi equals 0. And we have written delta phi last time. This is just the differential dual to the differential in the normalized bar resolution. Well, first of all, this condition delta phi equals 0 is exactly as follows. That we have G1 phi over G2 G3 minus phi over G1 G2 G3 plus phi over G1 G2 G3 and minus phi of G1 G2. This should be 0. Well, this should be 0 for all G1 G2 G3. This is exactly condition of cocycle condition. This is exactly condition delta phi equals 0. And well, this is exactly dual to the differential in the bar resolution. And one important moment, one important detail, since I prefer to work with a normalized bar resolution, I also should add a condition that phi of G1 G2 equals 0 whenever one of the elements is unit. Whenever at least one of the elements G1 or G2 is trivial. So C2 of GA consists of all functions phi which satisfies this condition, and the condition that we are in the kernel of differential delta is exactly this cocycle condition. But now, to understand the cohomology, we also need to describe this cocycle delta from C1 to C2, but we also have written formula for it, and formula for it was as follows. If we have here a function f, which is now a function from G, well, f is a function from G to A, exactly with the same condition that f of 1 is 0. Well, then delta f of G1 G2 is G1 f of G2 minus f of G1 G2 plus f of G1. Okay, so the second cohomology, which we are interested in, which enters our theorem, is exactly the quotient group. We take the quotient group of all functions phi satisfying this condition by all functions of the form delta f. So all functions which are obtained by this equation, they satisfy this condition. But we need to take all functions phi satisfying this condition, the kernel of delta, and we need to take quotient by all functions of this form. And this is exactly our cohomology group. Now, I would like to see the we would like to find a relationship between this situation and this situation, and this situation for an extension. First of all, I claim, well, here phi is just an arbitrary function. Here phi is particular function which appears from the construction. So we have an extension, we choose a set theoretic section, and we arrive to this particular function phi. So first claim 1, is that this phi obtained from an extension, this phi satisfies this cocycle condition. So for any extension, this phi satisfies this cocycle condition. Let us check this. The idea is how to check this. This cocycle condition is obtained from the associativity condition. This function phi measures how far is S of G1, G2 from being a product of S of G1 and S of G2. Now for three elements, G1, G2, and G3, we can compare S of G1, G2, G3 of such product to compare it with this product. And we can compare them in two possible ways. And this will exactly give us the cocycle condition. Let us check this. So, I will rewrite this condition here, this definition, and erase everything from this blackboard. So I just rewrite this and I erase everything here. So, okay, I can study such an element, S of G1, S of G2, S of G3, S of G1, G2, G3 inverse. And I can rewrite this element in two ways. First way, I can first write as follows: S1, S2, S G1, G2 inverse, and here S of G1, G2, S of G3, S of G1, G2, G3 inverse. Okay? Then we see two summands of this form. And we can write this as I of the following element. This one is phi of G1, G2. And this one is phi of G1, G2, G3. Okay? Here I have plus since, I recall that for A we use additive notation, for E we use multiplicative notation, so I takes sum to the product. That's okay. Well, but now I can, this is the first possibility to write this element. I can write the same element using second possibility. So this is exactly also for this element, this equality. I can write it, okay, I would like to replace this one by S of G2, G3. But here it is slightly more complicated. It is not, the matter is that these two are not in the beginning, so we also obtain some conjugation. I can write it as follows: S of G1. Here I write S of G2, S of G3, S of G2, G3 inverse. But here I write S of G1 inverse. This is conjugation. And here again S of G1, S of G2, G3, S of G1, G2, G3 inverse. Of course, this is a correct equality. I just add, these two can be deleted and removed, and these two can be removed, and we get exactly what we started from. So of course, this is a correct equality. But now we again see two elements which are phi's. Well, but what is this? This is the action. So what is inside is I of phi of G2, G3. But this is conjugation by an element which lies in the preimage of G1. This is exactly the action of G on A. So what we get here is I of G1, which acts on phi of G2, G3. This is this term. And from here, we get phi of G1, comma, G2, G3. Well, since I is an inclusion, we obviously see that this sum is equal to that sum. But this is exactly our condition. So we see that associativity immediately gives us this co-cycle condition. Is it clear, or do you have any questions?
How do we remove S from G1?
Well, how we define the action of G? No, general question. How G acts on A? We take a preimage and we conjugate a conjugate of this element by means of any preimage of G. So this is exactly as in the definition. So we do not need to remove this S. We just need to use it. Okay. So we see what we see. We see that to each extension, I briefly write extension. I mean an extension of G by A, which gives the prescribed action of G on A. Yes? To an extension, we assign a co-cycle phi. Now we need to see, well, of course, this construction is not canonical. It uses we need to choose a set theoretic section S. Well, what does this mean? This means that we need to find out how our co-cycle phi changes if we change a set theoretic section. So let us replace a set theoretic section with another set theoretic section and investigate how the co-cycle changes. So I erase this computation. This computation, it can seem not so easy, not so short, but the main idea is that it is very standard. So it is just a very standard way to do things like that. Well, okay. Now assume that we replace a section S by another section, S prime. Suppose that S prime is another set theoretic section for the same extension, of course. Another set theoretic section. Well, first of all, what does it mean? How we can relate two set theoretic sections? this means that if we write S prime of G and S of G, then I want to relate them. I claim that their quotient, well, of course, I have right quotient, a left quotient, for instance, this quotient. What can we say about it? We can say that it lies in the kernel of pi. Since S and S prime are both sections for the same pi, then this element lies in the kernel of pi. Hence, it lies in the image of I. Okay? So I can write that it is I of some element f of g, where f is a map, just map, not a homomorphism, just map from G to A. Any two sections necessarily are related by such formula. We just take this element and then it belongs to the image of I, hence we can write it as follows. Well, I always forget to check one important but simple condition. We need to check this normalization condition. I forget about it, but it is very trivial. If either G1 or G2, if at least one of them is 1, then of course this is 0. Yes, since we have 1 here. You just noticed that phi is normalized, so we have no problems with it. Well, and here this f also is normalized. The matter is that when I choose another theoretic section, of course I want it to satisfy the same normalization condition for 1. So of course for g equals 1 we have here 0. So f of 1 is 0. Now let us compare the cocycle phi corresponding to S and the cocycle phi prime corresponding to S prime. So we have the first cocycle is given by, this is the definition of the cocycle phi. Well, and we can write the same definition for the cocycle this is exactly the definition for phi prime. And we would like to express phi prime from phi and f. Okay, this is not so hard. We just need to substitute here. Okay, S prime G, I can rewrite this formula as this times S of G. Okay, I just put this here, and what I get that this I would like to write this element here. What I see here is exactly I see here I just write it, I of f of g1 times s of g1. Oh. Then I have I of okay, f of g2, then s of g2, and then I see this element with inversed. So I first see S of G2, G1, G2 inverse, and only then I see I of F of G1, G2. Okay? Yes, inverse. And inverse here means exactly minus here. Okay. What can we say about this guy? It would be wonderful if I can exchange, if I can move this to here. Then in the between I will see exactly phi of G1, G2. Yes? But, well, how to do this? Yes, we can do this, but this means exactly that we apply G1, to, that this we should replace this element by a conjugate. So we can rewrite this as follows. I of f of G1, I just rewrite this. Then I write the conjugate to this, I of G1, which acts on f of G2. Then, now, when I swap this, I see S of G1, S of G2, and this inverse. This is exactly I of phi of G1, G2. And then I see this one of minus f of G1, G2. Here we have a multiplication. What we see is exactly, now I takes sum to multiplication. So I can rewrite this as I of f of G1 plus G1 times f of G2 plus, I first want to write this one. It doesn't matter since well, A is an abelian group, so I can write it in any order, f of G1, G2, and plus phi of G1, comma G2. Well, this is just a simple calculation. And we see that this one is exactly what is written here. And this means that phi prime minus phi is exactly an element of this form. So, phi prime of G1, G2 minus phi of G1, G2 is exactly delta f of G1, G2. So what we see? We see that actually extension and section S, this pair, leads us to a cycle. But when we change S, when we change this set theoretic section, then we exactly add a co-boundary. We add delta f. So to an extension, for an extension, we have a well-defined cohomology class in this group H2, and this is exactly the cohomology class of this phi. The cocycle itself depends on S, but the cohomology class doesn't depend on S. Well, okay. What we see at the moment, we tried to prove. We are trying to prove the theorem. Theorem claims that, well, extensions up to equivalence. Of course, equivalent extension yield to the same homology class are in one-to-one correspondence with elements of this group. What we have done is the construction of the arrow from left to right. Yes, we show that for each extension we obtain a cohomology class. How to construct an arrow from right to a left? in a sense, this is the same question as how to restore the group E given the cocycle phi. And okay, suppose once again, suppose for a moment that we have such extension. Then how can we write an element of E? I claim that any element of E can be uniquely written in the following form as some element coming from A times some element coming from G, where A in A, G in G. Well, this is a trivial claim. Of course, any element which projects to the given element G can be uniquely written in this form for some A. So just we can write any element in this form. And we can, okay, I just want to introduce notation. Let us use another brackets, not to, I don't want notation to be similar to bar notation. It is another. Oh, just something dependent on two elements A and G. And how these such two elements are multiplied. Well, we need to make one more computation. I'm sorry for this, but okay, this is I of A1 times, A1 G1, A2 G2. I of A1 by S of G1, well, I of A2, S of G2. Again, it would be nice to swap these two, and to swap these two, I need to, I can write it as follows. I of AI, A1, I of G1 acting on A2, and then I get just S of G1, S of G2, and what is this? This one I can rewrite as just I want to do it in this way. I can rewrite it as I of phi of G1 G2 times S of G1 G2. Okay. This product by S of G1, S of G2, by using this formula, I can rewrite it in this form. What I get? I get all this belongs to A, to the image of A. So I get an element of the following form. I get again an element of this form. Where? Yes, thank you. Mine is here. No, plus. Well, we just move this. Well, what we see here, we see A1 plus, again I takes plus to multiplication, so plus phi of G1, G2, comma G1, G2. Look, the final formula uses just phi to define the multiplication in the group. So we can restore multiplication from using this phi. Note that if we remove this phi, then it is exactly the multiplication in semi-direct product. So it is very natural. It is exactly what we are going to obtain when the cocycle is trivial. Well, and in general situation, the idea is that now we can make the reverse construction. Now suppose we are starting from any cocycle, then we can restore the group E just in the following way. We, by definition, take for the elements of the group E are just such pairs, A, G, in brackets. This is just notation. And operation is like that. Of course, we need to check that this operation is associative and that this is a group. But, well, I don't want to do this. This is exactly the reversion of the computations I have done before. So this is a good exercise to use this, to look through the same computation in the opposite direction. And to see that, well, first of all, that if, what we need to check. First of all, that this is a well-defined group. So the multiplication is associative. And, OK, this is a group. And this is, once this is a group, this is automatically an extension of G by means of A. And it gives the prescribed action of G on A. And also, if we start, so this if we start with cocycles which differ by the same F, then we arrive to isomorphic subgroups just in different coordinates. Again, the same computation in the opposite direction. And so this correspondence is, and this arrow is in fact the inverse to the arrow we constructed before. So I don't want to go to spend more time for this. In one direction I was very precise, but the second direction is indeed the reversal of all this computation. So the general idea is exactly that that this abstraction to this is an abstraction for S to be a homomorphism, and this abstraction exactly is an element of the cohomology group. Okay. So, well, during several last lectures, I formulated several exercises. I hope I will unite them in some list of exercises or problems and will send it to you. Well, also a good problem, but maybe not so good formulated as, well, this is rather precise, but what is not so precise, a good problem is, well, what we haven't seen yet. A good problem is once, well, this is an abelian group. This is a priori just a set. But, well, a posteriori we see that this is the same group. So, a natural thing, we have an operation here. We can not think about cohomology group, we can just think about extensions. And a good problem is to describe the operation, to describe the addition operation in terms of extensions. So it is just useful to look what is the operation on this language. Well, we have it. So once we have here, so but it is useful to look how this operation works. Okay. What is next? Well, So once we have this theorem, now let us look in more detail on the case of central extension. So now I am interested only in central extensions. This means that the action of G on A is trivial, or equivalently, A is central in E. And in this case, as I have already said, we have cohomology with untwisted coefficients. And, well, there is one very useful tool, which is called universal coefficients theorem. For those who studied some algebraic topology, some homology and cohomology, the standard thing is that once we know integral homology of some topological space, or even of some free cell complex or free chain complex, then we can say something about cohomology with any untwisted coefficients. At the moment, I want to consider only untwisted coefficients. And, for those who don't know this, it is just a good exercise, since this is an exercise about the same functor which we have studied, but in a simpler situation. This is the exercise about functor x. But we have studied x over the ring ZG. Well, this is what we are doing last time, since I recall that just cohomology of group G with coefficients in A, this is by definition xk over Zg of Za. We have discussed this, and this was the general notation, but the simplest case is when the group G is trivial and we have no group G at all, and then we have just x over Z. I would like to be precise here. There is one bad thing with notation. I denoted xg. This is the same, by definition, the same as x over zg. So if I write x z, we can think of it in two ways. We can either think that maybe we take group G infinite cyclic, or we take G trivial, and then we get the ring Z. So this is for trivial G. Let us be precise. So we work just over integers, over the ring of integers. For a group G, I always use multiplicative notation. So this Z is just group ring for a trivial group. And in this case, I recall that only x1 exists. The matter is that working with Z modules is exactly as is only just working with abelian groups. And for any abelian group, A, we always have a projective resolution and even a free resolution with only two terms, F0 and F1. Well, this is just the standard fact that any subgroup of a free abelian group is again free abelian. So we just take any free abelian group which maps to there with surjection, and kernel is again free abelian. And hence all resolutions can be chosen of just length 1, and hence we have only x0 and x1. x0 as always is just home, but we have this x1 over z, and in this situation it is just denoted by x without any indices. And okay, the universal coefficients theorem, this is as follows. Suppose that we have free chain complex of abelian groups. Then we have the following. For each I, we have the following exact sequence. For each k. Yes, and A is just an abelian group. So in this simple situation, we just have n abelian groups and always work over Z. So we just have this x1z. Here we have cohomology groups. Oh, here, sorry. I would like to write it for any chain complex. Cohomology, well, what is cohomology of C star? This means that cohomology of home from C star to A. Well, and here we have home from kth homology of C star to A. Okay, this map is a standard pairing of between cohomology and homology. And we have pairing to A. This one is somewhat more involved, but okay, for those who don't know this, this is a very good exercise just for understanding what we are working with, for understanding properly this functor x. Moreover, this sequence always splits, but, well, this sequence is canonical, so it is functorial in C star, in A, but the splitting is not. So it all.
What is exercise?
Exercise is to prove that this sequence is exact. Well, this sequence is exact, and this sequence is called universal coefficients theorem. It more or less allows us to understand the cohomology of the complex, starting from homology of this complex. Well, as usually, we starting from any chain complex, we can take cohomology to some, or we can take cochain complex by taking home to some abelian group A, and then cohomology of this cochain complex can be more or less expressed from homology. More or less, since of course, if we know such, if we know only this exact sequence, it is not true that we completely know this group. Well, exact sequence splits, but it splits not canonically, so sometimes we do not know some things, but mostly it allows us to compute cohomology starting from homology. Yes, this is the first exercise, that this sequence is exact, and second, this sequence splits. Splits means that, in fact, this group is a direct product of this and this. But once more, the splitting is not canonical. So it is isomorphic, but this we cannot choose this isomorphism to be canonical, to be factorial. Okay, but, well, I'm mostly, yes, and of course, now, instead of, this is very general claim. It holds in very general situation just for any free, any complex of free abelian groups. But of course, for examples of such complexes, we can take chain complexes corresponding to spaces. So we can write here homology and cohomology of any topological space. So for any topological space X, we will have this sequence. Just this is, when I don't write coefficients, I mean integral coefficients. We can take this X, then we have cohomology of X with coefficients in A, then we have hom from homology of X to A. So and again, this sequence splits. And in particular, the same holds for any group. But since we know that homology and cohomology of a group is exactly homology and cohomology of its Eilenberg-MacLane space, so we see here the same. This hom is just over Z, just as abelian groups, and X is also over Z. So we have this universal coefficients theorem, and this is exactly what we are interested in. Yes, but everywhere in all these situations, coefficients are untwisted. So this is for untwisted coefficients. So the action of G on A is trivial. If the action is non-trivial, then we have no such direct claim. Okay, but what can we say now? Looking on this theorem, I'm mostly interested in second cohomology. And further, I don't want to study this term. And for not study this term, there is one very good condition. This term obviously doesn't matter if this group is trivial. And this is the case, so I'm interested in groups such that H1 of it is trivial. So this is a useful definition. The group is perfect if H1 of this group is trivial. And I recall that we already discussed that the first homology is just the abelization of the group, the quotient of the group by its commutator subgroup. So this exactly means that the group coincides with its commutator, and this is the usual notion of a perfect group. In algebra, without any homology, they usually say that a group is perfect if it coincides with its commutator. Okay, so starting from this point, assume that G is perfect. Then, taking K equals to 2, we obviously see that this term is 0, and so this natural factorial homomorphism is an isomorphism. So in this case, for a perfect group, we have a factorial isomorphism. For any A, we see that the cohomology is canonically isomorphic to the homology of the second, to the home from the second homology group to A. So in this situation, this is not in general situation, but only in the situation of a perfect group. Well, and now, look, we are in a very, very interesting and important situation. Well, it is the most, when we speak about cohomology groups, the most important, we usually think of this cohomology as a contravariant functor of the group G. Well, no, this is the most natural way to look on this. But also a very important point of view is that this cohomology group is a covariant functor of the coefficient group A. So let us look on this as on a covariant functor. So this one is a covariant functor of A. So now let us fix G and consider different abelian groups A. And we see a very important situation, that this covariant functor is always isomorphic to home from some special elements to this A. This is a situation well, what I want to say. What I want to say here. This is a standard situation, which is one of the, this is one of the situations when so-called Yonnet dilemma. I don't want to discuss a general claim, but it's in this situation. I want to say that okay, if we consider it as a covariant functor of A, then we have the most important case when here we put the second homology group. And in this, I claim that in this group, here, there is a universal homology class. So there is a universal homology class U here with the following property. Universality means the following property, denoted star, that for any A and any cohomology class V of the same G, G is fixed for G, we fix G. There exists a unique homomorphism F from this homology group to A such that V is a pullback of U. Sorry, what does it mean? Well, why pullback? I'm sorry. Just yes, it's lower star. Let's push forward. Okay. Let us understand why this claim is very trivial. So once more, the idea is that once this cohomology group is given by these homes from certain special element to an arbitrary element, then applying this functor to this special element, we find this universal element. In this functor, this claim doesn't use the specific property, it uses no specific properties of this functor. The same is true for any functor. If we have a functor of an abelian group which satisfies such condition, then we would have an element, any functor to sets. We would have an element in this functor applied to this special element, which is universal in this sense. And now, well, how to construct this element? To construct this element, we just need to apply this isomorphism and just need to take, okay, here, if we put H2 of G here, then we see that cohomology of G with coefficients in H2 of G is naturally, it is important not only this, we have this isomorphism, but we have this factorial isomorphism. It is factorial in A. So we have, in particular, we have a fixed, I will just write this equality since it's canonical. So we have canonical isomorphism to home from H2 of G to H2 of G. And here we have the identity home from H2 of G to H2 of G. It is an element here. And of course, we have the corresponding element. We have a corresponding element here. And this is exactly our U. Now look, if we have any, let us check this universal property. It is just very immediate. If we have an element of the second homology group of G with coefficients in A, then again using this isomorphism, this means that we have such homomorphism. But this is exactly F, and this F is exactly the homomorphism corresponding to V. If we have an element V, then there is a homomorphism F corresponding to it, and this homomorphism F, of course, takes the identity homomorphism to this F itself. This one corresponds to this U, and this one corresponds to V. So we see this formula. So this is just a simple categorical claim that if once we have such natural factorial isomorphism for all A, then we definitely have this universal class U, which satisfies this universal property. And now, what we are interested in, now let us recall that this is not only the second homology group, but this is the group consisting of all equivalence classes of extensions. So once we have this, the most important cohomology class, then we have the corresponding extension, corresponding central extension. So we have universal central extension we have universal central extension I would denote this particular E by G tilde. This is an extension of G by means of its second homology group. And it is a good question, how can we rewrite this condition star on the language of extensions? Well, first of all, in fact, what just if we apply this immediately, if we apply for any cohomology class, this means for any central extension, we have a unique homomorphism. There exists a unique such star, such arrow, yes, which takes one equivalence classes of extensions to another equivalence classes of extensions. What does it mean? This means that there exists also this arrow. But look, in fact, uniqueness of this arrow doesn't follow from immediately. Well, we only say that there exists such. Actually, there could be several maps here which provide the same mapping in cohomology, which take extensions to equivalent extensions. But next claim is that still in this situation it is unique. Why? Look, suppose that there are two such arrows which make the diagram commutative. Well, but then difference between these two arrows, well, they differ by such an arrow. Since they both make diagram commutative, then this means that if we take the quotient of these two, well, suppose that this one is well, Xi and eta, yes? Then if we take Xi of H is from here, multiplied 8 of H inverse, then it always belongs to the kernel, hence belongs to the image. So we would obtain this arrow, and moreover, of course, this such composition would be trivial. This is central, so This one would be trivial, since this would be a difference between this arrow and itself. Both arrows xi and eta make this square commutative. So if this one corresponds to the difference of this xi and eta, then this composition is trivial. Hence, we in fact get such an arrow. And such an arrow cannot be non-trivial because G is perfect. G is perfect, it coincides with its commutator, and so it has no non-trivial homomorphism to abelian groups.
Why do we have these arrows?
Once more. General claim, general universal property says to us that for each, we have this universal extension, and for any central extension here, we have a unique map here, which can be included in a commutative diagram. But a priori, we do not have uniqueness of this arrow. So assume for a moment that there are two different arrows, xi and eta, both making this diagram commutative. Then I would like to consider quotient of these two homomorphisms. Just, I would like to take this one. And of course, this element always belongs to the kernel of pi.
One moment, is xi of h lies in y
And eta of h also lies in. So we suppose that we assume that there are two different arrows. In non-perfect case, this can be, there can be such situations. Assume that we have two arrows, both making this diagram commutative. Then I consider this quotient, and I claim that we get into the kernel of pi. Hence, we get to the image of I. So this is I of some theta of h, where theta is an arrow like that. But now look, theta makes this triangle commutative if here we take xi eta inverse. Well, so it takes this triangle commutative if here we have 0. This square is commutative with xi and is commutative with eta. If we take here the quotient of them and theta makes this triangle commutative with quotient of them, then 0 map makes this square commutative with quotient of them. So we see that this composition is trivial. Hence, this theta actually comes from a homomorphism of G to A, but we have no such homomorphisms since G is perfect. We have no non-trivial homomorphisms to abelian groups. So this homomorphism must be trivial, and so this theta must be trivial, and so we have uniqueness of xi. So here it is some specific situation with perfect group, and so in fact our universal property, let us fix this, that our universal property now is as follows, that for any central extension of G, this is any extension, there exists a unique such diagram. We have a unique arrows. Well, in fact, now we can forget about this part. It is only once we have unique such arrow, then this one is just a restriction. So we have unique arrows which make this diagram commutative. Well, it is a useful and interesting property, and we will discuss it in more details after a break. I'm sorry, I was too long today. And well, today maybe it will be somewhat instead of discussing some particular problems, I will speak about some results which are we will not use them in future, but it is convenient to speak of them now. Well, okay. Now let us have a break till 6:10. Okay. Okay. What we have seen? We see that generally, for a perfect group, if a group coincides with its commutator subgroup, then there exists one particular important universal central extension with the following property that, well, first of all, the kernel of this extension is H2, the second homology group of G. And second, this extension is universal with in the following sense. For each central extension of the same group G, there exists a unique homomorphism from G tilde to E, which makes the diagram commutative. Having this situation, of course, first of all, we would like to describe this universal central extension explicitly. We have not done it yet. We know only which group is here, but we have many. We can have many central extensions with the same group. This is one particular. Of course, this general definition completely determines this, but it would be nice to see it explicitly. But before doing this is possible, and we will see it soon. But before doing this, let us concentrate on some properties of this extension, namely on some properties of G tilde. Well, and the first thing which I want to mention is that this G tilde is also perfect. So, claim is that G tilde is perfect. Well, let us discuss why this is true.
Why G tilde is even a group?
Oh, well, it is a group by definition of an extension. When we speak about extensions, we mean that all these are groups. So this is a group in which this H2 of G is central in it. We know that G is perfect, but I claim that G tilde is also perfect. Well, let us discuss why this is true. Well, look, assume that it is not. Длинная точная последовательность для гомологии чего?
Ну, этой точной тройки.
Нет, для точной тройки у нас нет последовательности. У нас есть спектральная последовательность, которую мы пока не обсуждали. Вот. Так что можно это достать. Yes, it can be obtained from a spectral sequence corresponding to this short exact sequence, but we have not discussed this yet, and this is a much easier claim than the Linden-Hornschild-Serre spectral sequence. So let us not discuss spectral sequence at the moment. Well, assume that it is not. Then it has, what means that a group is not perfect? It means that it has a non-trivial homomorphism to an abelian group. Well, so let us consider this extension. And we have a non-trivial homomorphism to some abelian group A. Well, I don't write that it is non-trivial. It is not zero. It is, and of course we can assume that it is surjective. We just may replace an abelian group A with the image. So we have a non-trivial surjection on to an abelian group A. Well, but we know that we have no such homomorphism from G. So I'm sorry, this is so easy that I forget the proof. I was concentrated on the second claim, but I forget about why it is. Yes, well, yes, we can take the composition we can take this composition from H2 of G to A, and then what we see, first I would like to obtain, I would like to prove that this one is zero, yes? Well. Yes. Assume that we have. I would prefer to write it as in this way. We have A here. Then. Let us consider such trivial extension. Okay? This is a central extension. Well, and our universal property says us that there is a unique homomorphism from here to here and from here to here, which makes diagram commutative. But I claim that I know at least two. First possibility, I can take here, let us denote this, this F is this, okay, this standard homomorphism. Not the standard, those homomorphisms which exist by our assumption. Let it be F. Well, first of all, I can take 0 here, this I, this pi, and pi here, pi 0, okay? Let us forget about this F. We always can take this. If we have any group A, then we always can take this, and the diagram is commutative. This is definitely true. But now assume that we have an untrivial homomorphism F here. Then I claim that there is another possibility. Instead of taking 0 here, I may take the composition, I composition with F. Instead of taking pi here, I may take pi F. Look, the diagram is still commutative. Okay, if I take these two homomorphisms, just I take this composition here, and I take pi on the first, and phi f on the second. Then this is commutative. So for the same extension, we have two possibilities. This contradicts our universality property. we must have only one. So there are no non-trivial homomorphisms from G to A. So here we have, if there were such a homomorphism, we would have a problem with uniqueness. Not with existence, but with uniqueness. Okay, but now the second, I recall that perfect means its first homology group is trivial. But обман? Где обман?
Нам как бы сверх, тогда гомоморфизм из второй гомологии var должен быть.
Нет. No, here this one is not given. Just for any extension, there exists and unique these two arrows. No given homomorphism to A. Yes, and actually look, whenever this extension is trivial, whenever here we have G times A, then this homomorphism, of course, is trivial. Yes, this is just. But it turns out that if there were such a homomorphism F, then we can find here non-trivial examples, and that's not good. Okay, so G tilde is perfect, but moreover, perfect means the first homology group is 0. Next, I claim that the second homology group of G tilde is also 0. Such groups are called superperfect. Well, by definition, a group G is superperfect if and only if it is perfect and its second homology group is also 0. And so G tilde is superperfect. So let us prove this. Assume that this is not true. But then for a moment, I would like to erase here. We have this extension, but if the second homology group of G tilde is non-zero, then we can consider this similar universal extension for G tilde. Let's consider it. Then we would have the second homology group of G tilde. Here we would have some G tilde tilde, G tilde, and 1. Okay? Assume we have this. But now let us consider the composite extension in the sense that, of course, G two tildes is an extension of G tilde. Oh, of G. We just take the composition of these two projections. G tilde is extension of G. G second tilde is extension of G tilde. Look, in the case we consider arbitrary abelian extensions, such composition of two abelian extension can be not an abelian extension. Maybe the kernel, maybe not abelian. But in the case it is central, this means that these elements commute not only with elements from here, but with all elements of G tilde. So in particular with elements from here. So this is again a central extension. So this one is again central. Such composition of central extensions, always central. In central extension, we add elements which commutes with everything. If we twice add elements which commutes with everything, then it's okay, they still commute with everything. Well, but now, what we see? Now let us use our universality property. So I just erase the middle.
When do we understand that it is central?
Well?
When did we understand that it is central?
This one? No, we started with studying central extensions. And we found out that they correspond to cohomology with untwisted coefficients. So all extensions central, except for those. Well, this one is constructed, and we check that it is central also. All these extensions are central by their definition. Okay, now I would like to erase the middle term and use the universality condition. We know that this extension is universal, and this is also a central extension of G. So we have a unique, but now I don't need a uniqueness. I only need that we have such arrows which make diagram commutative. Well, but what does it mean? This means that I erased it, but we have this. It is not so good that I erase it. I write it once more here. Okay, we have this projection. And we have this map from G tilde to G double tilde. I claim this is this map lambda. I claim that lambda is it is inverse to pi tilde in the sense that if we apply first lambda and then pi tilde, then it is the identity homomorphism of G tilde. Okay, why? Just because here why this is true? Well, the matter is that, okay, we have here pi tilde, yes? Well, and so if lambda, then lambda composition with pi tilde is the classifying homomorphism for the same, for this universal. Okay. Well. When we say one general note, that when we say about this universality property, I don't need to mention this group at all. I just would like to say that for each central extension, but it should be central, of G, this universal extension has the following property, that for each central extension of E, there exists a unique such arrow which makes diagram commutative. Then this arrow always arises as its restriction automatically. So we may speak just on this. So let us not look here, but if this lambda was not a right inverse of p tilde, then this composition, let us take E equal to G tilde. Then this uniqueness says that only identity isomorphism makes the diagram commutative. If we would But this lambda p tilde also makes the diagram commutative. So it must be identity. Okay, but once we have this identity, we see that this is a direct product.
Why does pi tilde composed with lambda make this diagram commutative?
Why this? Because lambda makes this diagram commutative. And pi tilde makes that diagram without lambda commutative. This map was defined to be pi tilde composition with pi. We originally take for this map we originally take this composition, pi tilde and then pi. So without lambda it is commutative by very definition, and with lambda we just this is just a construction of lambda. So we see this equality, but now what does it mean? This means that this sequence splits, and since it's central, it just means that G twice tilde is a direct product of its second homology group of G tilde times G. But it is impossible. The matter is that, okay, if G tilde is perfect, then of course G twice tilde is also perfect by the same argument. So it has no homomorphism to abelian groups. But this one is abelian. So we cannot have non-trivial homomorphisms to abelian group. So the only but the projection on the first multiple is such a homomorphism. So the only possibility is that the second homology group is in fact trivial. So we see this fact, and we see that fact. Well, and it turns out that such superperfect groups are very interesting from topological point of view, and I will explain why in a moment. But now let us start with constructing this universal extension explicitly. I will give the construction, but I will not prove that the thing I construct is indeed universal. To prove this, you need to go through two proofs. Well, we have two things. We have, first of all, we know that if our group G is written by generators and relations, we have a presentation of it. In other words, it is written as a quotient of a free group. Then we know that the second homology group can be naturally identified with such a group. Well, can be canonically identified with this. We have proved this last time, and today we have constructed this this universal extension in this way, as it is written. Taking this together, I will give the answer, but the proof that it is exactly what we obtain, we need to follow those two proofs. The proof of this fact and the proof which was today. And this is a good problem to look through them and to understand that what I will write is exactly the answer. And I suggest you to look through this problem yourself. It is very useful. But the answer is as follows. Okay, we know that our group is F. I will write it in this form. We know that it is such quotient. Okay? Also, we know that the second homology group can be written in this way. In the middle, I can put just this group. I take the commutator subgroup of F, and I take the quotient by the commutator, this mixed commutator subgroup. I claim that this is exactly this universal extension. As I promised, I will not prove that this is exactly universal extension, but let us at least see that this is a central extension. That, let us prove that this lower row is exact, and that it's first that it is well defined and exact, and second that it is a central extension. Okay, look, what can be non-trivial here? Well, first of all, it is well defined. Subgroups, we have already discussed that this is well defined. This subgroup is obviously normal in the subgroup, in the commutator subgroup. It is normal. Okay, why? Because okay, it is obtained by a. It is not even a normal. It is it is obtained by canonical construction for a normal subgroup N. So it is preserved by all automorphisms of F, which preserve N. But all inner automorphisms of F preserve N. So this one is invariant over all inner automorphisms. So it is normal even in F. So it is normal in these commutator subgroups as well. Of course, we have homomorphisms of numerators, and they induce homomorphisms of the whole. Here N is of course greater than this one. Oh well, sorry. Which one? Yes, N of course contains this one. Yes. Yes, because this one is normally defined by such commutators, and this one belongs to N, and this one belongs to N. So we are in N. So at least these maps are well defined. Now let us prove that this is an exact sequence. What is obvious? First of all, it is obvious that this one is injective, since it is injective on numerators. Somewhat less obvious, but still easy, is that this one is surjective. Here, it is not true a priori. It is not true for any G, but it is. It follows immediately from the fact that G is perfect. What means that G is perfect? it means that any element of G can be expressed as product of commutators of elements of G. This means that any element of F can be expressed as a product of commutators of elements of F up to elements of N. So we see that since G is perfect, this means that any element of F is a product of commutators and elements of N. So, taking any element here, we can change it by elements of N so that it gets into the commutator. So, this is surjective. Okay. Now, next, as usual, the most non-trivial part is exactness in the middle term, but one part of it is trivial. If we take the composition, then it is of course 0, since this n goes to the denominator. We just take the quotient by all relations. So this is trivial, and the only thing we need to check is that this kernel actually coincides with the image, is not greater than the image. And I would like to look on my notes. Well, in my notes I only wrote that it is trivial. Well, let us look. This is indeed trivial. So, assume that we have an element here, some xi, which goes to 1 here. Let us look on this xi as an element of commutator. Let us take an element of commutator, some, okay, which letter A? A is an element of commutator, which goes to 1 here. What does it mean? This means, well, let it be just W. It is just an element of a free group. We prefer to think of it as of a word. So let it be W. So what can we say about the word W? First of all, it belongs to the commutator. What does it mean? It means that if we, let us introduce some notation. We have, let G be given by generators x1, xk, and relations R1, Rn. So that x1, xk are exactly generators of f, and n is normally generated by this R1, Rn. So this W is just a word in x1, xn, and their inverses. And first of all, what does it mean that this word is in the commutator subgroup? This exactly means that if I count the number of x1s in this word, then the algebraic number is 0. And the same for x2 and the same for x3. The matter is that the commutator for a free group is exactly the kernel of such map. This is exactly the commutator. So this is exactly all words which go to 0 here, where this homomorphism is just counting homomorphism for variables. Okay, so first of all, number of xi equal to the number of xi inverse for each I. But now this word goes here to a trivial element. What does it mean? This means that this word, no, it goes to the trivial element. Yes, it goes here to a trivial element. What does it mean? It means that this word belongs to n. So it belongs to this. So it comes from here. So it is actually trivial. Yes. Even we do not need this this characterization of a commutator. It belongs to the commutator and it belongs to n, and so it definitely belongs to here. So this is the exactness here is actually trivial. Well, but I claim that if we follow all this construction and follow through this proof of this fact, then we arrive immediately to this is a good exercise problem. This is problem in the sense of well, it is exercise, but it is not as easy as an exercise should be. That it is exactly a universal extension. But we have also one more. We have also another description of this group, which is sometimes which is due to Sergei Novikov, and which is sometimes it appears in his work on one topological application of this thing. I will speak on this in a second, which is slightly more convenient. Why this is not convenient? Because this commutator is not finitely generated. This group, this presentation of this group is very inconvenient. It would be nice to have a finite presentation for this group, starting from a finite presentation for G. Well, this one is not. But I claim that we can rewrite this in the following form. Let us consider the following. Well, these R's are relations, but in fact, it is very easy to see from generators and relations that whether this group is actually perfect or not. Well, the matter is that to obtain an abelianization, we just need to write the same generators and the same relations, but in an abelian group. So when a group is perfect if this is just linear algebra. If we take the same relations, but think of them as of relations in an abelian situation. The best possibility for this is to replace multiplication by addition. Let us take the same relations, but replace multiplication by addition. Then we should obtain zero group. So x1, xk must be expressible from this in abelian situation. What does it mean in non-abelian situation? In abelian situation, I knew that, for instance, x1 is obtained if I take 5 times r1 and 3 times r2, for instance. Well, then I can just write the same word, r1, r1, r1 5 times, r2, r2 3 times, in non-abelian situation. What I get? I will not get x1, but I will get a word which such that these count and homomorphisms such that it contains algebraically exactly one x1. The number of x1s is 1 greater than the number of x1 inverses. And for all other xi's, the count and homomorphism is 0. So, and the same for all other generators. I claim that there are the following, that if G is perfect, and we are in this situation, then we can write the following words: S1, Sk, and these are some words in relations. And similarly here, we can write these words so that if we look, if we take these words in X's and substitute here, so we get lone words in X's, well, so if I count the algebraic number of xi's, the algebraic, this n xi means the number of xi in a word minus the number of xi inverse in a word. This is just notation. If I take this number in Sj, then I get 1 if I equals j, and 0 if I is not equal to j. Well, so if G is perfect, then we can find such words. More or less, we can find them. It is an easy algorithm how to find it. We need to look on this as an abelian group, and it is a standard fact about abelian groups that if it is 0, then we can express xi's from ri's. Okay, once we do this, I claim that G tilde, the same G tilde, can be written in the following way. For generators, I take the same generators as in G, so it will be the quotient of the same free group. But I have another set of relations. Concerning relations, I write here all commutators of all such commutators where I take a generator and a relation in G. So if I have k generators and n relations, I have kn relations of such type. This should be, well, this relation means that this is equals to 1, yes? But also, this is not enough. Also, I need to write down these special words S1, Sk. And this is a complete answer. The claim is that G tilde can be written in this form. So let us understand what I want to understand. I want to understand that this guy is isomorphic to this guy. Let us see in which direction we have an arrow. Well, where is it? Again, write only that it is. Well, in which direction we do have an arrow? So we have this one, and we have this quotient. Well, I claim that we have an arrow in this direction. Well, if, first of all, if we have the commutator subgroup of F, then of course we can include it into F itself and then map to this G tilde. But let us understand that this guy goes to 1. Well, okay, this joint commutator subgroup is normally generated by these elements. So it definitely goes to 1. Okay? So this one is well defined, but claim is that this one this is an isomorphism. Well, first let us understand that this map is surjective. Why? And here we again need the fact that I already mentioned, that any element of G tilde, any element of G, is a product of commutators, and hence any element of F is a product of commutators and elements of N. So we can write any elements here as a product of it is important that G would be perfect if we take only these relations. These relations are weaker than initial set of. Initially we have all Ri's, but if we take only these relations, the group will still be perfect. So any element of F can be written. We have a stronger assertion that any element of F is a product of commutators and product of elements S1 as K in some order. The matter is that F quotient by S1 as K is perfect. Hence, this assertion. So, each element of commutators can be written, each element in G tilde, S1 as K are relations in G tilde. So we can add them to, we can take an element of G tilde, write it as any word, and then we begin to add elements S1 as K in such powers that all counting homomorphism becomes 0. And we get into the commutator. So this is surjective. A more interesting question is why this one is injective. Well, and here we need to proceed as follows. Just let us try to proceed by definition. We take any element in the commutator, any element A here in the commutator, and assume that it goes to 1 in G tilde. Again, not I prefer to think of it as of the word W. What does it mean? Look, this means that this word W can be written, once it goes here to 1, it is written as, it is not true that it is written as a product of these relations. It is true that it is a product of conjugates of these relations. Once an element is 1 in G tilde, it follows that this word is product of conjugates to this element. So let us write it down. W is a product of conjugates of elements of this form and elements of that form. Besides, look, elements of this form are very nice. They belong to. If we had only elements of this type, we would be done. They belong to f of fn, and if we have a product of elements of this type, then we indeed are in the denominator. So our w is, we don't want to prove that w is a trivial word. This is not true. We want to prove that w is here. Hence, an element in this group is trivial. So, if we had only elements of this type, it would be fine. But we also have these elements. But look, we also know that this element f belongs to the commutator. Hence, if we count the number of each xi in this element, in this word, the algebraic number would be 0. But look, at every such element, it is also 0. But at every Sm, it is like that. This means that in this product, so we may write y as product of some conjugates. So it looks like that. We write it as product of some elements, but each of elements looks, it is some word v. Here we have some commutators like that. And here we have v inverse. So for instance, we can have multiple of such type. So here we have multiples of two types. One type is v xi rj xi inverse rj inverse v inverse. This is first type. And second type is v some maybe other u word s j u inverse. And here we have plenty of words of such type. Yes, of course, they also are in powers plus minus 1. And what does it mean that this w is in the commutator? It means that each sj is here 0 times algebraically. Each sj gives exactly one xj. So each sj is exactly one time. And it is good once we have this one. We can always so for each sj we have something in between, and then we can with different u we have sj inverse. And then we can rewrite as a commutator of sj which with what is in between. So up to an element, and here we can get rid of this sj. This is a normal subgroup, and we take quotient of this subgroup. Using quotient, using element of this group, in this group there is a commutator of this element in between and sj. And we applying these relation, there is such relation in this group. So applying this relation, we can get rid of all sj's. Well, we have inverse here, but we can include it. Yes, this. Well, so this is a scheme, and you can think through this scheme in more details. It is very difficult to write in a blackboard. Well, but the claim is as follows. And now maybe in just more briefly. I don't want to speak about this in details, but why it is important. I have already mentioned, maybe last time or maybe the time before the last time, that when we work with topological spaces, a standard situation is that it is easy to compute homology, and it is difficult to compute homotopy groups. But it is rather easy and algorithmic to compute homology. We just take any cell decomposition and do some linear algebra. But for the groups, it is not true. If we are given a group explicitly by generators and relations, if we have a finite presentation for them, then if we try to compute homology by definition, we need to work with bar resolution or with some other standard resolutions. But, well, any standard resolution which works for any group is something about bar resolution. We do not have canonical better choice. And then it is infinitely generated, even if a group is finitely generated. It is extremely hard to work with it, not only extremely hard, but it is algorithmically impossible to work with it. And there is result like that there is no algorithm that allows, given a presentation, a finite presentation of a group G, allows to compute H2 of G. This is a result due to Gordon 90s. So there is no algorithm. There is no algorithm to understand whether this group is trivial, whether this, for any reasonable, and the same for higher homology group. So except for the first homology group, we cannot say algorithmically, we cannot say anything algorithmically. But it turns out this was noticed by Sergei Petrovich Novikov, and it is a very important very important observation, that though we cannot, given G, we cannot find out H2 of G algorithmically. However, we can write, given a finite presentation for G, we can write a finite presentation for G tilde algorithmically. So though we cannot compute H2 of G, we can kill it. What is this? This is a group in which we kill the H2 of G. We take the extension which is super perfect. So we cannot compute it, but we can kill it algorithmically. And this is a crucial observation. This is a direct recipe for this. We just take, it is just immediate. We take this one, computation of SIs. It is not canonical, but it is very explicit. We just solve problem in abelian groups. In abelian groups, all problems are easily algorithmically solvable. We express xi's from r'i's in abelian sense, and we take these expressions in non-abelian setting. So we write down these SIs, and then we immediately have an answer. So we can produce a finite presentation for G tilde explicitly. Why this is interesting? This is interesting since it allows to prove the following topological result. It is a famous theorem by Sergei Petrovich Novikov. And theorem is like that. Theorem says nothing about groups. Theorem says that for n greater than or equal to 5, the sphere is algorithmically unrecognizable. Algorithmically unrecognizable. this means the following, that suppose you are given a manifold in some algorithmic form. For instance, you are given a triangulation of manifold. I don't want to discuss now some, there are some details, what is a triangulation of a manifold, which triangulations we consider, which not, but at least it is more or less clear that if we are given a triangulation, this is something which is accessible for a computer. We have under a manifold, I mean closed compact manifold of dimension n, so we have just a finite simplicial complex. And you ask whether this complex is homeomorphic or piecewise linear homeomorphic. It doesn't matter in this set. For instance, homeomorphic to Sn, to the sphere. And the claim is that if n is at least 5, then this there is no algorithm which decides whether it is homeomorphic or not. Well. Since I have mentioned this topic, I would like to say that for n equals 3, there is such an algorithm. For n equals 2, you can find this algorithm yourself. You just need to compute a Euler characteristic, and yes, and that's enough. More or less. Well, but for n equals 3, there is such an algorithm. It is not so easy. It is a great. It is related to problems considering knots, and you may ask whether a knot is an unknot, whether it is trivial, and it is in the same field of problems. So the complete algorithm is due to Rubinstein, and it is 1990s. And for n equals 4, it's completely open. The corresponding question is completely open. Whether this question is algorithmically decidable or not. But I don't want. I always need to finish very soon, so I don't want to be precise here. But why? What is the role of this claim in this proof? I just give some scheme of a proof. There is an explicit construction. Assume that you have a group and it turns there is a more or less explicit construction which allows to do the following. So assume that this group is superperfect. Superperfect groups are very important at this setting. So that the first two homology groups are trivial. Then you may just take the standard sphere and start attaching handles using some special algorithm. So you just attach, first of all, you attach handles of type dn, boundary of dn times okay, you take here two holes, well, and attach a handle which is interval times Sn minus 1. Then you attach, these are handles of index 0, then you attach handles of index 1 along relations, and you attach some special handles of index 2. And claim, which I claim is that the result is a manifold M with the following properties. First of all, it's homology sphere. this means that the homology of this manifold are exactly as those of the sphere. And second, the fundamental group of this manifold is by construction the given group pi. So there is such explicit construction by, you can just glue these handles and obtain such a manifold. Well, look, there is a very important thing that in dimensions 5 and greater, we have a generalized Poincaré conjecture. We have it in all dimensions, but at the moment of this theorem, there was only dimensions 5 and higher. But still, though we know it's in all dimensions, it is important and greater equal to 5 in the construction. So this theorem says that this theorem is due to Smale in dimensions 5 and higher, and it says that once we have this and trivial fundamental group, then this is a sphere. It is homeomorphic to a sphere. If it is group is non-trivial, then of course it is not homeomorphic to a sphere, since it's not simply connected. And another ingredient is a result by Sergei Ivan Chadyan of 55, that the property of a group to be trivial is algorithmically unrecognizable. So given a presentation of, this is a purely algebraic result, you are given a finite presentation and you are asked whether this group is trivial or not. The answer is there is no algorithm. There is no algorithm deciding whether G is trivial or not. Well, and now all these ingredients are enough. Look, assume that you had an algorithm that recognizes whether a manifold is a sphere or not. Then I suggest to you an algorithm which recognizes whether a group is trivial or not. We take a group, and first of all, we look whether this group is perfect or not. This can be done algorithmically. We just need to write down the same generators and relations in abelian setting, and this is quite algorithmically to decide whether it is trivial or not. Yes, so whether G is perfect or not. If G is not perfect, then of course it is non-trivial, and we are done. Suppose it is perfect. Then we apply this construction and get another group, which is super perfect. But look, this G tilde is trivial if and only if G is trivial. Well, of course, it is greater than G, so if G tilde is trivial, then G, of course, is trivial. But if G is trivial, then it is also trivial. So we come to another group, G tilde, which is trivial if and only if G is tilde. And we take this G tilde for pi. We apply this construction. And then we, it is important for this construction that it is super perfect. We apply this construction, and we get a manifold. And then we apply our hypothetical algorithm, which says, okay, this is a sphere or not. If it is a sphere, then by generalized Poincaré conjecture, we know that the group is if it is trivial, then if it is a sphere, then we do not need any conjecture. If it is a sphere, then we know that the group is trivial. Yes? If it is not a sphere, then by generalized Poincaré conjecture, we know that the fundamental group must be non-trivial. If it were trivial, it would be a sphere. So we know that G tilde is non-trivial, hence we know that G is non-trivial, and we are done. Well, so actually, though I skipped this topological construction, it is more or less direct, and actually this is the most non-trivial part of the theorem. This idea that that one can kill the second homology group by means of this construction. Well, this is just some topic which is not very close to our situation, but in some sense it explains us how well it is one such things related to such algorithmical topology is one of things why superperfect groups are interesting. And also I would like to mention such open problem that look here, of course, okay, there is such construction, but in fact we even do not need an explicit construction. We need only a fact that there exists a homology sphere. What is written here is called a homology sphere. A manifold is called a homology sphere if it has a homology of a sphere. And the only claim we need is that in dimensions 5 and higher, for each finitely presented group pi with which is superperfect, there exists a homology sphere with the prescribed fundamental group. I claim that it is enough. Why it is enough? It is enough since, well, assume that we do not know this explicit construction involving handles. It doesn't matter. A general idea in such situations is that if we know the existence of something, we can usually construct this something algorithmically. We just try to take for this M all possible finite simplicial complexes. And for each of them, okay, homology is algorithmically computable. We can just compute and check whether it has this homology. Fundamental group is not algorithmically computable. But it turns out that it is still not a problem. We know that the answer should exist, so we find only for positive answer. We try to find this fundamental group together with given isomorphism. And we are looking for such situations. It would be nice if somebody gives to us a simplicial complex together with a proof that this simplicial complex is manifold and it has this homology and it has this fundamental group. If there was such a proof, it would be a finite text. So we looked through all texts until we reach this proof. It is possible to make, well, and so what doesn't work in dimension 4? In dimension 4, we still do not know which fundamental groups arise as fundamental groups of homology spheres. In dimension 5 and higher, these are exactly all finitely presented superperfect groups. In dimension 4, it is not known. What is the characterization of groups, of fundamental groups which arise as, and if this problem is, if somebody solves this problem, then most probably it will give a solution or a good progress towards this algorithmic problem. Okay, so let's finish for today. I think it's too long.